Hey guys, I recently had an opportunity to talk to the researchers and engineers over at Hiad, which stands for the Hypersonic Inflatable Aerodynamic Decelerator, or what I like to call space brakes. It's very interesting technology. It's something that I would have never thought of, having an inflatable structure in space to slow down spacecraft.
Inflatable structures, in the general sense, is becoming very popular.
Yeah, but I understand it a little more in the HAB, because we do have decelerators now. We use parachutes. How does this? Are we still using parachutes? Is this a different thing altogether?
Well, we're using inflatable structures in addition to parachutes, because what happens is that the size of the spacecraft can only get so big, and after it gets larger, you need a decelerator that's going to go ahead and slow it down.
So with the inflatables, that structure can go beyond the spacecraft and slow it down.
And I'm just assuming, I'm sure we'll find out in the story, that the inflatables weigh less than, like
that's
your
the big
normal,
thing. That's the big difference.
Now, are they partnering with those inflatable moonwalk things that kids use as part of a technology partnership, or is that separate?
Are you talking about moon bounces?
Yeah, moon bounces, yeah.
No, I doubt it.
I tell you what, let's go check out the segment on Hiad.
Just checking.
I'm here with Neil Cheatwood, Principal Investigator for Hiad. Exactly what is Hiad?
Well, Hiad stands for Hypersonic Inflatable Aerodynamic Decelerator. And let me break that down for you. When we go to other worlds, we have to launch from Earth, and then we have to decelerate. And we can do that either propulsively, like we did at the moon with the lunar module, and use just engines to slow us down. But if it's a world with an atmosphere, then it makes sense to make use of that atmosphere and the atmospheric drag. And so what we do is we actually wrap our payload, what we're taking to the surface of the planet, we wrap that in what we call an aeroshell. We're currently limited to the size of aeroshell that we can do based on the rocket size. So our aeroshell has to fit inside that rocket shroud. And so the idea is, if we could deploy a larger aeroshell out of a given rocket, then we could take down more mass and actually get more payload to the surface of Mars or Venus or wherever. What we're working on here is a hypersonic version of that, where we deploy outside the atmosphere, but then we have to handle that heat pulse, the high deceleration pulse that we see when we go into the atmosphere. So that is a hypersonic inflatable aerodynamic decelerator.
One of the big parts of Hiad is the inflatable structure. So tell us a little bit about how it is constructed.
Okay, well, what we have here is a stacked torus, and the way you make a torus is you braid a tube, and then that tube then has a liner, a silicone liner inside of it, and you inflate the tube, and it becomes a torus. And if you stack the tori together so they intersect or interfere with each other, they become a pretty rigid structure, which you can see over here. We have to protect the structure from the heat of reentry, so we apply a thermal protection blanket. The outside is a Nextel fabric, which we've quilted together. And I'll take this ring off and show you the way it's constructed. The fabric itself keeps the integrity of the outer structure. Then we have an insulator ply, which you can see is this powdery yellow surface in here. That takes the outer surface heat and knocks it down to a temperature that the bladder can tolerate. And we have these gas barriers beneath it that prevents inflow of the hot gases. The hot gases on the outside are wanting to drive to the low pressure. Behind her in the wake region of the aeroshell is a very low pressure. So the pressure on the front wants to drive through, so we have to put a gas barrier behind it. And this is a test sample for running in the 8-foot high temperature tunnel. We've instrumented it with some thermocouples so we can see what the various temperatures are in between the layers, and we can match that up to the models that we've done for prediction to see how well the TPS performs.
Should we explain a little bit more about why you would use an inflatable reentry system versus the old rigid thermal heat shield?
We've been to Mars, as an example. The first time we went was in 1976 with Project Viking, and there was a big technology development program for Project Viking. They developed a TPS material called SLA 561V, which is super lightweight ablator, 561V for Viking. We've actually used that on every successful Mars mission since then, and here we are in 2011. And so we've been using all that technology all these years, but we've been sending more and more stuff each time. So the payloads are getting bigger. In actuality, our next mission to Mars is the biggest payload we've sent there, the Mars Science Laboratory, and we had to switch our TPS materials because it was getting so heavy. And even with that, we can only land at what was below sea level at Mars because we're just coming in too fast, we're too heavy. So the idea is to make a larger drag device so that we could land that same mass at a higher altitude or take more mass to the surface. So it's all about size. Size does matter.
Your next test coming up is IRV-3. Tell me about that.
IRV-3 is another suborbital flight. We've had IRV-2, which is our first successful demonstrator. V3, we've increased the mass of the payload so that we can get about twice the heating applied to the aeroshell. And this time we're going to require a TPS. The last time we just had the fabric to show how well it's stowed and whether it would survive the rigors of packing. This time we need to demonstrate that we can pack with the insulator. And the insulator is a fairly low density material, so we need to make sure that we can pack it down very tightly. And it's also a fairly delicate material, so we need to make sure that it doesn't fall apart when we package it and then later deploy it.
Neil, tell me about where we might be able to use this technology.
We can use the aeroshells where we have a sensible atmosphere. And when I say sensible atmosphere, it has to be enough that really means anything. The moon does not have a sensible atmosphere. That's why we landed using retropropulsion. Mars has what I call a poor excuse of an atmosphere. It's very thin. It's the most challenging destination for us because it's actually too thick an atmosphere to ignore. We don't want to just take rockets and land on the surface. It's not very efficient. But it's so thin, it's like 100,000 feet here at Earth. It's very, very challenging. But we can use this technology at Mars. We could use it for Earth return. We could bring stuff back from space station. We could bring stuff back from the moon. We can use it at other atmospheres like Venus, the gas giants, Jupiter, Saturn, Uranus, Neptune. Titan, which is the large moon around Saturn, has a very thick atmosphere. So it could be used at any of those locations.
We've done some studies and demonstrated that these are enabling technologies for way out there where we're doing a manned Mars mission. They're talking about landing 40 metric tons of payload on Mars. Right now, there's absolutely no way to do that. Well, these aeroshells are potentially a technology that will allow us to do that once we figure out a way to get 40 metric tons to Mars orbit. So that's another challenge.
That's a big challenge.
It's a big challenge.
But you're up to the challenge.
Oh, yeah, we're on it.